and thank you for tuning in. Welcome to a new episode of the Passion for Technology podcast by EBV Electronic.
Welcome to the Passion for Technology podcast. When we think about how technology is evolving, we often imagine faster processors, sharper displays, or more intelligent algorithms. But behind many of these advancements lies something less obvious: light. Not the kind that illuminates a room, but light as a signal, a sensor, a switch. Optoelectronics have become essential to how machines perceive the world and how humans interact with machines, powering smarter, safer, and more intuitive experiences. Today on the Passion for Technology podcast, we're pulling back the curtain on this invisible enabler with a deep dive into optoelectronic innovation at Vishay. From factory floors to car dashboards, from subtle sensor feedback to robust isolation and power systems, their components are everywhere and evolving fast. We're joined by three experts from Vishay's Opto division to unpack how these technologies work, where they're headed, and why they're becoming indispensable to modern design. Jörg Wedermann, Vice President of Product Marketing, is joining us, as is Mohan Kanusami, Director of Product Marketing, and Sami Ahmed, Senior Applications Engineer at Vishay's Opto division. It's fantastic to have all three of you here today. We're diving into the fascinating world of optoelectronics, and I'm excited to explore this invisible technology that's powering so many of our modern experiences. Well, are you guys ready to shine some light on this topic for our listeners?
Sure.
Awesome.
Yes, we are.
Excellent. Mohan, let's begin with the basics. What types of components do customers typically source from Vishay Opto?
So at Vishay, we do have a very wide range of products in our portfolio at Opto. So basically, when you think about optoelectronics, it's always like, okay, we have like infrared emitters, for example, that emit infrared light. And we also have photodiodes that detect light, either it's visible or infrared light. And we also have visible LEDs in our portfolio. And there are things like also combination of emitter and detector, for example, a reflective sensor. So you have it in the same package. Or we have digital sensors to detect presence or light sensing. And this is on one side, and we also have optocouplers for electrical isolation. And there are things like IRDC transceivers, for example, because it used to be big in those days where you have for data communication. And now actually we do also supply these IRDC transceivers. And finally, and then we have like for infrared receivers, which is also in what we see in every day. In your television set, when you switch on your remote, they have like the receivers that's on the other end in your TVs, to receive these modulated signals. So we do have a portfolio of infrared receivers. That's what I said about wide range. So we have it in a full portfolio of optoelectronic components.
Sami, help us bring this technology into the real world. Mohan has already started with that. Where are these components commonly used? Where else? And why would anyone rely on optical signals in the first place?
So sure, Mohan already mentioned that we've got optical components in applications we use every day. There's the remote control of the television. There's the receiving part of the television that allows you to control the TV to begin with. That's probably something everyone has used in their life and is maybe aware of the fact that it's optics doing what's happening on the television. However, it moves into other applications as well. A mobile phone gets turned on or off with the screen so they don't accidentally push a button in a call, because an optical sensor is turning off that screen when you're putting it to your ear. If you're driving in the car and it starts to rain, it's usually an optical sensor detecting that raindrop and turning on the windshield wipers. Maybe most people aren't aware of this. That comes due to the fact that it's in an application area that you don't usually look into, as well as that, as you mentioned before, it's not visible light doing the sensing, but invisible infrared light. That's really helping the signal be detected and used for the purpose.
Thank you, Sami. Vishay Opto has a rich history. Jörg, can you walk us through some of the milestones that shaped the division?
Yes, thanks. And indeed, it goes very long way back, all the way to the 1960s, with the foundation of Telefunken, one of the pioneers in Germany for semiconductor development and product manufacturing. And then starting with an LED, the first LED manufacturing in 1970. We worked on lasers before, developed the first optocouplers for isolation requirements, and then eventually became part of the Daimler concern, forming Telefunken Microelectronic And eventually in 1998, we have been acquired by Vishay. And since then, we're developing further the portfolio, focusing on optical components, as Mohan mentioned, embracing infrared emitters, photodiodes, phototransistors, receivers, still visible LEDs belong to that range, of course, in the development. And in 2014, we acquired Capella Microsystems as a step into the digital world of these discrete optical components, sensors, and other devices. And with that, we were basically enriching our portfolio, including IC developments, making the devices smart, making them sensors with some intelligence inside, to the latest milestones of opening our new gallium arsenide wafer fab in Heilbronn. It's a great commitment also to keep the technology in our hands to develop infrared emitters in-house. And the last one is with the acquisition of an 8-inch silicon factory of Vishay from Nexperia, where we are now developed also photodetector technologies, being capacity ready and utilize this factory as well.
I find the outlook really interesting, Jörg. I mean, you've mentioned how the company progressed, what steps and milestones you guys have went through and how you're progressing. I'd be really interested in understanding a little better what truly fuels the rapid pace of innovation today.
Yeah, and we are excited about the developments as well. The mega trends are boosting the demand, mega trends such as electrification. Electrification, not just in the sense of automotive and electric vehicles, but also with regards to renewable energies, which require a higher robustness level of optocouplers to provide the necessary isolation and isolated switching characteristics of these parts. On the other hand, when we look into the automotive world, it's about autonomous or towards autonomous driving, where the features in the car needs the sensors for driver monitoring systems to make sure the LiDAR systems are working with optical encoder for scanning LiDAR applications. Towards HMI, human machine interface, there's a lot of displays coming into the cars, complemented with still turn-ups, and all of these need sensors to detect the interface, the interaction with the driver, with the passenger, and together with the increasing connectivity of smart devices, which all require a certain state and sensor input, being detecting a proximity for signal wake up or being an ambient light sensor condition, temperature, humidity condition, all boosts the demand for these new sensor developments.
Semi, optical switching can seem almost magical to those unfamiliar with it. Could you break down the fundamentals of how it works? I'm curious about the design flexibility, how adaptable these systems can be for different applications.
Sure. And you touch a good point with the flexibility, because that's really one of the main factors that drives optical design. So the magical aspect, of course, comes from the fact that you don't see the light coming out and going back in. If you compare that to traditional mechanical switches, there you actually have to push something, you see something moving. So one of the main factors is that there's no moving parts when you're using an optical sensor or when you're designing for optical switching. As a general concept, just so you can grasp what's going on, light is emitted out of a component. It reflects back from any given surface. Usually in the human-machine interface, it's a human hand, but it can be anything. And we'll touch a bit more on different uses of that a bit later. It gets reflected back into the sensor, and then a photocurrent is generated. This is an analog output, and you use that current to trigger something or see the change in something, be it light in the surrounding or something coming closer. That, however, can also be, as Jörg mentioned, with the acquisition of a digital, something an ASIC has, it can be digitalized, and that digitalization can allow for some signal conditioning, just making the component more reliable, more capable, and really, in the end, easier to use in a circuit. So the concepts of light stay the same. However, the use of the signal generated by the light is where the innovation lies.
I find that really interesting. Sami, looking at the spectrum from non-touch to force touch solutions, what's in your portfolio? And I'd be really grateful if you could help our listeners connect the dots. Where are they likely to encounter these technologies in their everyday lives?
Sure. Now, you've mentioned a couple of buzzwords there with non-touch, touch, and force. Maybe I'll shed some light on how the general concept works and give some functional examples. So when it comes to touchless, this is maybe one of the more graspable or traditional use cases of an optical sensor. Light is emitted out of an application. It actually leaves the application, and you are inclined to not actually touch the end application. It reflects off your hand and goes back into the device. From the Corona times, though I'm happy they're over, hygiene was a big topic. And if you think about a soap dispenser, oftentimes it's an optical sensor detecting something before it's actually touched and dispensing soap. Or in the same way, it could be a water faucet being turned on. Similar use cases are also found in touch panels, for example, where you don't actually want fingerprints to be on the panels. You can have that trigger beforehand. The second type of switching, you actually want touch to happen. It signals some sort of intent. You can do some aesthetic design, for example, backlight a switch with a white LED. And in this case, you've got the sensor calibrated to only detect if the user actually touches the surface of the device. So swiping across it or coming close to it will not. And it eliminates the sort of false detection where touchless sensing in some applications might actually cause an issue. If you picture that in a car, you're just moving your hand across from the steering wheel. All of a sudden something switches. You don't want that to happen. You actually want to move towards the device and actually select your functionality. And similar things apply also to home appliances where the actual touch of the button is the intent. And the most recent use of these kind of reflective technologies is what we call force sensing. So here, similar concept again, light comes out, light comes into the sensor. However, a material is positioned above the sensor, and the way that this material bends or deflects towards the sensor can relate to an amount of force that is applied to that material. So you're basically bending a material that's usually in a given position towards the sensor. The signal increases. And it's not about just it changing to a high or low. You actually want to detect a high resolution increment of this change so that you can monitor that change and make use of a three-dimensional application, or in most use cases at the moment, to signalize true intent and avoid false detection. Picture a capacitive button. You accidentally touch it, it triggers something, and you're frustrated about that. If you were to force the user to apply some force to that material, you could make sure that it is actually what's intended. And the nice thing about these kind of applications is it's extremely flexible in its design. You can use it with any type of material. You can post-design it in. The material can be already in place, and now all of a sudden the user wants some functionality out of it. You can retrospectively put it in there, see that we get some mechanical stack-ups in place, and off you go. You already have a smart surface.
Thank you, Sammy. Now you've covered quite the breadth of potential use cases and applications. I'd like to double down on the automotive world. I mean, we all know it's known for being particularly demanding when it comes to reliability and performance. What unique challenges do you encounter when developing touch-based interfaces specifically for vehicles?
So you say touch-based. This also applies to the force and the touchless that I mentioned before. And the key driving factors are always robustness and reliability in the automotive realm. So that comes down to our part qualification. But from an application point of view, it comes down to a lot of design considerations that, when put into place correctly to begin with, allows for a very, very robust and long-living solution. Because again, there's no actual moving parts. So the main challenges that sort of our sensors would encounter are, for one, the big factor in almost any electronic device is temperature. That accounts for signal drift in our devices, where a signal is generated by temperature rather than by light, and that needs to be compensated for in some way. As we're so often really close to the human-machine interface, our sensors encounter light in the same way that a human encounters light. Sunlight, for example, has a very high infrared content. Now, our sensor needs to be able to differentiate between what the sun is sending, which we don't want to trigger the device, and what we're sending out, which we do want to trigger the device because it is reflected back into the sensor. And there's some circuit considerations you can do and some implementations that can help remedy this, which at the end has a very low signal to noise ratio. Basically, what am I wanting to detect and how do I get everything I don't want to detect, ambient features of some sort, to not disturb our signal? And with analog devices, much of this is done in the circuit design. There's things like tolerances you need to take into account. The nice thing about digital sensors is not only can you do some trimming and some calibration in the part whilst it's manufactured to reduce part-to-part tolerances, but you can also implement remedies for these temperature effects and these ambient effects into the device. So our proximity sensors, for example, will measure the amount of light and temperature and take that out of the equation before you even measure the signal out of the device. So it's just making things more smart.
In what other ways does Vishay's optoelectronic solutions contribute, or do those solutions contribute to automotive innovation?
So we've talked a lot about reflective sensing. Mainly, most of what I've touched on is proximity sensing. That's what goes into switches. We also have implementations of infrared emitters and photodiodes separately to one another. Things that come to mind are the rain light tunnel sensors, whereby light of the surrounding, be it in a tunnel or sunlight, rain is detected through the emission of light onto a surface and how that surface changes due to, for example, a water drop dropping on it. The same thing is with ambient light sensors. So ambient light sensors don't focus on the emission of light. They have a filter on it that detects surrounding light and tries to assimilate that which a human would see. And that's necessary for backlight dimming and display dimming of all sorts, because we need that contrast to fit so that when we look at a display, we see what the display wants us to see. In the case of optical isolators, where light doesn't actually get emitted from the component, but stays within the component, we have a lot of safety features in which these components are being used. Exactly what Jörg touched on earlier with the sense of electrification in automotive. We have a high voltage battery that needs to be monitored. It needs to be pre-charged and discharged. We have voltages that need to be taken into account so that we don't have high inrush currents. Everything to make it safe for the user to use the car. And also there, it's an optical signal doing the separation and really doing the heavy lifting of the safety application.
Vishay has a global footprint with operations spanning multiple continents. Mohan, how do you orchestrate that international collaboration to take a product from initial concept all the way to market launch?
Right. So as any global company, we do have a presence worldwide. Like Jörg mentioned at the beginning, because I think we have our new factories and we're based here in Heilbronn, Germany, where our divisional headquarters is, where we have our front-end production, where we have our gallium arsenide and silicon chip production. And then we also have our engineering, planning, marketing is also based here. And we also have our R&D hubs in Taiwan, in the US, and also in our back-end factories in Malaysia and Philippines. So combined, actually, it's something like a follow the sun model, because I think where one region passes on, so just to accelerate the development. So when you have an initial idea, it starts here from product marketing alignment, and then we start working together with our R&D teams to develop an initial product concept. And of course, we develop together with the global teams to bring down a new product to the market. And one of the latest new products where we have our new product currently under development, where the infrared emitter and the photodetector comes out of Heilbronn, Germany. And then this design, of course, is being done in different locations in the US and Taiwan and in Germany, the chip designs. And then this part is actually then assembled in Philippines. And actually a key part of the ASIC comes from Taiwan. So it is really a global development. And in the end, actually, when you see the package, it has the footprints in every continent, almost.
That's good. That's a very tangible description. Jörg, imagine you're in an elevator with a potential customer who's never worked with Vishay before. What's your compelling case? What's your elevator pitch for why they should partner with you for their optoelectronic needs?
I think it's a very simple but strong statement. We are your partner. We are not just a supplier. We act as a partner. And what enables us to act this way is exactly what also Mohan and Sami described before, also based on our history. We are vertically integrated. We have our own chip development and manufacturing in Heilbronn from the emitter side, the detector side. We have our own IC design. We have our own package design and manufacturing. And all this in combination and understanding the processes and the product and the interaction of all the individual components that eventually make the product enables us to act as a partner and give the best support on the product and on the application that you can imagine.
So once a customer decides to move forward with Vishay, what does that collaboration actually look like, Mohan? What should they expect from working with your team?
So in the end, it's always like solving their customer need, right? So I think the customer comes up with a requirement. So we do have a very collaborative process. So actually in the end, in the first, actually we start with asking what the exact issue is or exact requirement is. Then we integrate our multiple teams, because then we have our application team just getting to know about what the exact requirement is. And then once we have understand the requirements from the customer side, then we work with our R&D team to develop a proof of concept. And also we create out some prototypes just for the customers for the evaluation. And once customers are satisfied with this part, then we start from our side, go in parallel with the projects. And of course, it's not just it stops there. We work together with them throughout the life cycle of the product, right? So we start with them from the beginning, from the idea till the product goes into production. And then, of course, till the end, we are there for life for the customer.
Jörg, for listeners who might be intrigued by what they're hearing today, whether they're engineers, product developers, or decision makers, what's the most practical way for them to explore your technology hands-on?
First of all, of course, visit our website, follow us, contact us through our tech support contacts to get directly in touch with our technical team. We have a lot of reference designs, evaluation boards where you can experience hands-on how the sensors work and help on the design, accommodated with the necessary technical collaterals. And of course, we are present at all big fairs and trade shows where we usually demonstrate our sensors and have live demos where everyone is welcome to visit our booth and start a discussion with us, along with trying out how the sensors work.
All right, so here's a fun one to close out our technical discussion. If you could educate the world about one aspect of optoelectronics that's often misunderstood or overlooked, generally not known about, what would it be? Any takers?
Maybe I can start with this one. Since we share all the same passion for optoelectronics, what I would like to see is the awareness of the people that they are using this technology, this invisible technology, actually in their daily life without knowing how or what kind of innovation and technology is behind it. So by simply switching on the TV, as Sami mentioned at the beginning, it's based on infrared signal. It's a decoded signal on the TV side, and everyone is using it without thinking about it. It just works. It has been working so robust for decades and has been developed further into more complex sensor environments. For everyone, it's self-taking that the wiper turns on when it starts to rain, but there is a lot of innovative optoelectronics behind it. And the sense for that is where we would like to wish more understanding, because it's a kind of a hidden champion, if you will, versus everyone talks about microprocessors, memories, that's in everyone's thought. But optoelectronics is the hidden champion that enables a lot of functions in our daily life.
And maybe to add to that, there's so much of our senses, of our actions governed by the sense of sight. That is what optoelectronics brings into devices. So the closer we want to get to having these devices perform tasks in our everyday life like we do, the more we need optoelectronics in these devices to see them like we do.
Just one thing about also with this, we talk a lot about smart homes and smart devices nowadays. Like Sami said, our Opto products acts as an eye. I mean, anytime you see a robotic vacuum cleaner just going close to your stairs and not falling down, it's basically, it senses, because there we have something like cliff detection or a collision detection. So basically it senses this environment and it works properly. So that's why it becomes smart in the end.
And what really comes across, and I think what also came across or comes across for our listeners, is that you're all passionate about optoelectronics in particular, but technology in general. And that's where I usually, as part of our show, ask you about the origins of your very individual passions for technology. How about we start with you, Jörg? Where does your passion for technology come from?
The passion started 27 years ago already, or even before that. I started with doing my master thesis back then in my physics studies on optoelectronics, optimizing infrared LEDs based on a certain material system. And since then, it caught my passion, bringing not just the electronics on the technology side as part of the understanding, but also in combination with light. And that gives the certain magic we have been talking all the way now in this podcast. It's bridging distances from PC board to PC board. There is an infrared emitter. No one can see it. At one point, there's a detector detecting it. So out of electrons, you form photons. Photons will be turned into electrons again. Signal is transmitted. You can use it for data transmission. You use it for light barriers, and everything is just invisible. So the magic portion of the enabler of optoelectronic solution is basically driving, or has been driving, my technological passion for a very, very long time. And it will continue for sure.
Mohan, how about you?
Yeah, for me, it's about curiosity of how things work, yeah, and why. Basically, it still fuels because I think we see a lot of new innovations in the optoelectronics field. So like what we saw, all these examples, maybe it looks very simple. I think it's also for me, I think right from the beginning, it's always like why and how. So it's any new, right from the old TVs to like the new cars and then every new smart devices. So basically, I still have it. It still continues.
And Sami, what sparked your fascination with technology?
I think for me, it's more the word creativity. I'm basically one of the only engineers in my family. Most of them are creatives. And it came from PC gaming to wanting to understand how the electronics behind the PC works, to realizing that the whole thing kind of makes sense and you can apply things that make sense to something creative. And that combination of things sparked interest, continues to spark interest, and is innovative, which always fuels my passion for such a thing. Yeah.
That hits very close to home. Well, thank you. That brings us to the end of this episode of Passion for Technology. A huge thank you to all of you, Jörg, Mohan, Sami from Vishay Intertechnology, for joining us and sharing your expertise with optoelectronics with us. Dear listeners, you can find more information in our show notes. Please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Jörg, Mohan, Sami, thank you all for joining us today.
Thank you.
Thank you too.
Thanks a lot.